So the last bit of this chapter deals with different types of forces within molecules and between molecules. And there are two different categories of forces. One is intramolecular forces, which are within molecules or ions, which we refer to as bonds, so covalent bonds, ionic bonds. And then the other one is intermolecular forces, which are kind of like what we refer to as attractive electrostatic forces. So it's the attraction between opposite charged species. Now with intramolecular forces, when you break an intramolecular force, you're destroying that substance. So for example, if we have sodium chloride, if you add enough energy, you can break the sodium chloride bonds, and then you would no longer have sodium chloride. Likewise, for covalent bonds, if you put sugar on a stove, eventually you will decompose the sugar by breaking the carbon-hydrogen, carbon-oxygen bonds, for example. So when we're breaking intramolecular forces, we're destroying that substance, that the bonds that hold that substance together, the individual entities of the substance. And so as you can see from the table, intramolecular forces are very strong. So for example, ionic bonds, the energy to break it's anywhere between 400 and 4,000 kilojoules. Covalent bonds anywhere from 150 to 1100 kilojoules. Even metallic is pretty strong, depending on what type of metal, 75 to 1,000. So kind of remember this, because on the next slide we're going to show you intermolecular forces, and you'll notice that those energies are a lot lower. So again, it takes a lot of energy to break intramolecular forces. Now, in regards to physical states, what we're doing is we're weakening or breaking intermolecular forces. And so this is the attraction that occurs between molecules or molecules and ions of different substances or the same substance. And so it's this attraction that holds them together. So as you add energy, you break it, but you're not destroying the molecule, for example. Now, as you can see from the energy shown in the second to last column, these are a lot lower than the intramolecular forces. If you remember, the lowest intramolecular force was metallic, which was 75 kilojoules. And here, only the ion dipole has something relative to a strong intermolecular force. The rest of them are very weak. Because here again, the charges between the different species are further apart than they are in intramolecular forces. And we're going to go through and talk about each one of these intermolecular forces, which are referred to as non-bonding interactions. And with non-bonding interactions, the interaction has to be within what's referred to as the van der Waals radii. And if you review over a previous lecture I just posted, it talks about what van der Waals radii are. So as long as this distance between the two entities is less than the van der Waals radii, it's an intermolecular interaction. Now, since it's not a physical bond, it's referred to as non-bonding interaction, because it's not an actual covalent bond. So with ion dipole, ion-induced dipole, and dipole-induced dipole, you're going to have two different entities involved. So for ion dipole, what you have to have involved is a ion from an ionic compound, for example, sodium or chloride, and they're going to interact with a dipole on a polar compound. So for ion dipole, you need an ionic compound and a polar compound. So the polar compound could be water, for example. Water is a polar compound. Or it could be methanol, any of your small chain alcohols like methanol, ethanol, maybe even propanol. Those are going to be polar compounds. You mix a salt with it, you get an ion-dipole interaction. And the ion-dipole interaction is the strongest intermolecular interaction out of all the ones listed. And so what happens is the sodium ion, for example, interacts with the partial negative charge on the water, which is the oxygen. So you have this sodium ion interacting with the negative part of the water molecule, which is the oxygen. And then likewise, the anion of the salts interacts with the positive side of the water molecule, which is the hydrogens. And that's where you get this ion-dipole interaction. To give you an example of where ion-dipole is used, if you've ever boiled water, sometimes you put salt in the water. As you put salt in the water, you're changing the intermolecular forces present, because water by itself is hydrogen bonding, but when you add salt to it, now you form ion-dipole interactions. So since you have a stronger interaction, it takes more heat to boil the water. And so that's what happens when you add salt to water. You form an ion-dipole interaction. So for ion-dipole, you need two different things. You need an ionic compound and a polar compound, polar solvent, for example. And the most common polar solvents are things like methanol, ethanol, water, even what we refer to as acetone. So if it's polar, it's going to have a dipole, and then you have an ionic compound which supplies the ion. Next, we have hydrogen bonding. Now, hydrogen bonding can occur between molecules of the same substance or different substances. So hydrogen bonding, you don't have to necessarily have two different entities. You just need to have certain requirements for a hydrogen bond to occur. And so those requirements are for hydrogen bonding is you got to have a hydrogen that's attached to a very electronegative element such as nitrogen, oxygen, or fluorine. So again, the hydrogen has to be attached to one of these three elements, and it has to interact with a lone pair of one of these three elements. So if the hydrogen is not attached to a nitrogen, oxygen, or fluorine, at least for general chemistry 2, it doesn't undergo hydrogen bonding. So for example, ammonia, NH3, would undergo hydrogen bonding because the hydrogen is attached to the nitrogen. And hydrogen bonding is a subset of dipole-dipole, but it's a very strong dipole-dipole interaction. And it's only exclusively for the most electronegative elements, nitrogen, oxygen, and fluorine. So again, the hydrogen has to be attached to a nitrogen, oxygen, or fluorine and interact with a lone pair of electrons on a nitrogen, oxygen, or fluorine. So water, hydrogen bonds with itself. So the hydrogen is slightly positive, the oxygen is slightly negative. They have this attraction to each other. Now, the shorter this distance is between the hydrogen on one molecule and the oxygen on another means the stronger the attraction is. And that's where you use van der Waals radii to determine how strong the attraction is by summing up the van der Waals radii to determine what's the maximum distance. Typically, hydrogen bond distances between oxygen and hydrogen range anywhere from about 1.8-ish to about 2.4 angstroms, in that ballpark. And the way you measure these distances is by using what's called X-ray crystallography. You get the X-rays of the crystal, you're able to measure the distance between neighboring molecules. So again, hydrogen bonding is a very strong dipole-dipole interaction, but just for a select few number of elements, only those elements that are the most electronegative elements. Now we get to dipole-dipole. Dipole-dipole interactions can occur within one type of substance, so it can have dipole-dipole within molecules of the same substance, or it can be two different substances. But the only thing to be dipole-dipole is that it has to be a polar molecule. So all polar molecules have dipole-dipole interaction. So what you'll do is you'll look at the molecule. If you assign it as polar, it'll be dipole-dipole. There's no ifs in that. So you look at a molecule, you'll determine it's polar, then it's dipole-dipole interaction. And what this is that in a polar molecule, you have permanent dipole moments. So you have a positive end and a negative end, and then that aligns with or interacts with the positive end of another and a negative end of another. And this is permanent dipole. Again, is found in only polar molecules. Now the next two, ion-induced dipole and dipole-induced dipole, for both of these you need at least two different entities. So for ion-induced dipole, of course you need an ionic compound. Induced dipole is for a nonpolar substance. So whenever you see induced dipole, that's referring to nonpolar entity. So you have an ion and a nonpolar entity, such as shown here, Fe2 plus and O2. O2 is nonpolar, Fe2 plus is the ion. That interaction would form an ion-induced dipole interaction. Another common example is if you try to dissolve sodium chloride in hexane. Sodium chloride is a salt. Hexane is a nonpolar solvent. So if you try to dissolve sodium chloride in hexane, it would result in an ion-induced dipole interaction. So again, you need an ion and you need a nonpolar molecule. And that's where you get this ion-dipole interaction. Now, dipole-induced dipole is similar to ion-dipole, except now instead of ionic source, you just need a polar compound and a nonpolar compound. So the dipole comes from the polar compound. The induced dipole comes from the nonpolar compound. So induced dipole means that it only has a temporary dipole. So the dipole keeps on moving within the molecule because the polarizable electron cloud moves. And it's not permanent. So that's why it's a weak intermolecular interaction. So the example they use is if we take HCl, which is polar, and mix it with Cl2, which is nonpolar, we get a dipole-induced dipole interaction. Another example is if you try to take, for example, water and hexane. Water is polar, hexane is nonpolar, so you would get a dipole-induced dipole interaction. And the last one, dispersion, or what we call London forces, occurs in all nonpolar molecules. So if you have a nonpolar molecule, the only intermolecular force it has is dispersion, aka temporary dipole, aka induced dipole. So again, all nonpolar molecules, the only intermolecular force they have are dispersion forces, aka temporary dipole, aka induced dipole. And these are very weak, so it doesn't take much energy to break them. And that's why, for example, fluorine, F2, which is nonpolar, is so weak, the intermolecular forces, that's why it exists as a gas at room temperature. Whereas something like water has stronger intermolecular forces, that's why it exists as a liquid at room temperature. So we're going to go through and explain each one of these intermolecular forces in more detail. So the first type of intermolecular force that we talked about was ion dipole. So again, the two components you need are in an ionic compound and a polar solvent. Now, the most common polar solvent is water, but there are other types of polar solvents as well. Things like methanol. Its formula is CH3OH. Ethanol, CH3CH2OH. Even acetone is polar. That is, give me 1 second, that is C3 H6O, I believe so. Yes. So these are just examples of polar solvents. And so if you try to dissolve an ionic compound in one of these polar solvents, you get an ion-dipole interaction. Of course, water is the most common polar solvent that we have. And so what happens is when you dissolve, say, sodium chloride in water, the anion chloride interacts with the positive side of the water molecule, which is the hydrogen side. The sodium ion interacts with the negative side of the water molecule, which is the oxygen. But it doesn't just have to be oxygen. Here, if we look at this lithium, we see that it is interacting with acetone. So acetone is a polar molecule. The oxygen is the negative end. So the cation interacts with the negative end, and therefore you get an ion-dipole interaction. So the two things you need are an ionic compound, which contains cations and anions, and a polar compound, which contains partial positive and negative charges. So those are the two requirements for ion-dipole. If you just have a polar compound, you cannot have ion-dipole. You have to have a polar compound and a source of ions, namely ionic compounds. Next, we have dipole-dipole forces. Again, all polar compounds have dipole-dipole interactions. So you may hear me use the word forces or interactions, referring to the same thing. I just use them interchangeably. And so this again occurs in all polar molecules. If you see something is polar, it's going to have dipole-dipole interactions. And so the way you know something is polar is that the dipoles do not cancel out. So here we have a molecule, maybe it's HCl. HCl is a polar compound. And so you have these permanent dipoles that are affixed in the solid state. They interact with the positive and negative ends of different molecules. So you get this dipole-dipole interaction. Now, when you start to add energy, you start to weaken these dipole-dipole interactions, causing it to convert from a solid to a liquid. Now, again, you're just weakening when you go from a solid to a liquid. You're breaking when you go from a liquid to a gas. And so this is a good chart because here we're talking about dipole moment and how it affects the boiling point. By the way, if you're ever in, kind of stuck between determining which compound is stronger attractive forces than another, the best deciding factor is the boiling point, because the boiling point will tell you, how much energy is needed to break the attractive forces. So the higher the boiling point, the stronger the attractive forces are. So boiling point is directly related to strength of intermolecular forces. So if you want to know which molecule or substance has the stronger intermolecular forces, you refer to its boiling point. Now, melting point is different. So you can't really use the melting point as a gauge because In the melting point, there's other factors that are involved, namely how the molecule packs as a solid. But boiling point, again, boiling point, what we're doing is we're breaking the attractive forces. So the higher the temperature, the more energy is required to break those attractive forces. And so as we look at these different compounds, we see first we have propane. And again, we're comparing what I'd like to say apples and apples. So all of these compounds have similar molar masses. If we're trying to compare things that have different molar masses, there are other rules that we have to obey. But if we're comparing compounds with similar molar masses, then the more polar the compound, the higher the boiling point will be, because the larger the dipole moment. So again, you got to compare molecules of similar molar masses. So we have propane. You'll notice propane only has carbon and hydrogen. So anytime you see a molecule with carbon and hydrogens, it's non-polar. The rest of these molecules are polar. So as you see, propane has very little dipole moment because it's nonpolar, compared to diethyl or dimethyl ether, which is a polar compound. You see it's almost 100 drop in the dipole moment, and we see that it has a higher boiling point. Next, we have methyl chloride. Again, a slight increase in the dipole moment. We have a slight increase in the boiling point. And the reason it's not as much is because chlorine is not as electronegative as oxygen. That's why there's very little increase between dimethyl ether and methyl chloride. Now when we get to acetaldehyde, again we have an increase in the dipole moment. We see an increase in the boiling point. And here, when you look at these, the red end is the negative, the blue end is the positive. And so the darker shaded red, the more negative that dipole end is. The more blue, the more positive. So the greater the distinction in the colors, the greater the dipole moment. So if you notice for dimethyl ether, it's a little bit of red here, and you have a little bit of blue here. So this is a negative, and this is positive. So very little shown. As we get to the next one, a little bit more. So again, the red signifies negative, the blue positive. Now when we get to acetonitrile, you see it's a very distinct dipole moment. This is the negative end, and this is the positive end. So since it's a very distinct dipole moment, it's very strong. It has the highest boiling point. So again, when we're comparing molecules with similar molar masses, the polar ones are going to be higher boiling points than the nonpolar ones. And then the polar one with the greatest dipole moment would have the highest boiling point. Now, when we compare molecules of different molar masses, then we have to use other criteria. So now hydrogen bonding, again, hydrogen bonding is a subset of dipole-dipole. It's a very strong dipole-dipole interaction involving, at least in general chemistry, two terms, the three most electronegative elements, nitrogen, oxygen, and fluorine. So again, to have hydrogen bonding, you need a hydrogen that is attached to an oxygen, nitrogen, or fluorine. So in this example, hydrogen is attached to an oxygen, and it's interacting with a lone pair on a nitrogen, oxygen, or fluorine. We go to the next example. We have a hydrogen that's attached to a nitrogen, oxygen, or fluorine that interacts with a lone pair on a nitrogen, oxygen, or fluorine. It can't be carbon It has to be one of these three elements. Even if we have a hydrogen attached to an oxygen, and you see it's interacting with the lone pair on a nitrogen. So all of these are examples of hydrogen bonding. Now you can have hydrogen bonding with the same molecules or hydrogen bonding with different molecules as long as it meets these criteria. So the hydrogen atom has to be attached to a nitrogen, oxygen, or fluorine that interacts with a lone pair on a nitrogen, oxygen, or fluorine. And hydrogen bonding is a very important interaction. It's used a lot in developing drugs with different types of pharmaceutical properties. Even in DNA, which holds DNA together, is hydrogen bonding. So it's a very important intermolecular interaction. And so if you have dipole-dipole, hydrogen bonding would be stronger than a dipole-dipole. And what makes water such an exceptional hydrogen bonding species is that for every water molecule, it can form 4 hydrogen bonds. So for example, the hydrogens on each water molecule interact with an oxygen, and then the lone pair on each water molecule interact with a water molecule. So you get this like tetrahedral arrangement of water molecules that surrounds one water molecule. And this was what makes hydrogen bonding so strong in water, because every water molecule can hydrogen bond to 4 other water molecules. Now, generally, as we said for a dipole-dipole, we noticed that the stronger the dipole moment, the stronger the higher the boiling point. But if we look at NH3, H2O, and HF, and we want to say which one of these would have the highest or the strongest hydrogen bonding, we would say, okay, the greater the difference in electronegativity, the stronger the dipole moment, the higher the boiling point. But what happens is since water can undergo this hydrogen bonding between 4 other water molecules, whereas HF can only hydrogen bond with 1 other molecule, or 1 on each side, then the ranking would be ammonia, HF, and H2O. So H2O has the strongest hydrogen bonding between these 3 listed here. Even though the electronegativity difference is greater between HF, the fact that the fact that water can hydrogen bond to 4 water molecules makes it a stronger interaction than just HF, which could only hydrogen bond to 2. 1 on an H interacting with an F, and a F interacting with an H. So this is weaker than water that can hydrogen bond with 4 hydrogen bonds per molecule, where this one only has 2. So even though HF has a greater electronegativity difference, since water can form more hydrogen bonds per water molecule, it has a higher boiling point than HF, aka stronger dipole moment than HF. It's just a chart showing how dipole moments and the boiling points differ. So for hydrogen bonding, or those compounds that contain hydrogen, we have H2O, HF, and NH3. And you see that H2O has the highest boiling point, meaning it has the strongest hydrogen bonding, then followed by HF and NH3. Now you see there's a significant drop in the boiling point as we go from H2O to H2S. And the reason is because H2S is just polar. It's involved in dipole-dipole. HCl is polar, but again, since it's involved in dipole-dipole, it has a lower boiling point than HF. Likewise with PH3, it's a polar molecule, so it's weaker than NH3, so it has a lower boiling point. Now, as you see, as we go from HCl to HBr to HI, the boiling points increase. The same thing when we go from PH3 to ASH3 to SBH3, the boiling points increase. Likewise for H2S, H2SE, H2TE, boiling points increase, and the reason is because the molar mass increases. And this gets into something we're going to talk about a little bit, but as the molar mass increases, the secondary forces in these molecules become stronger, and that's why H2SC is stronger than H2S, because secondary intermolecular forces are stronger in H2SC versus H2S, and we'll talk more about that in a little bit. And then if you look at CH4, which is nonpolar, it has the lowest boiling point out of its series when comparing it to the elements in the same row. Then we have silicon tetrahydride, germanium tetrahydride, and tin tetrahydride. So all of these are nonpolar molecules, the last row. So before we talk about the last intermolecular force, which is dispersion forces, we need to introduce another term called polarizability, which is what affects induced dipoles, or what produces induced dipoles in molecules. So polarizability is the way a nearby electric field can induce a distortion in electron cloud of an atom, ion, or molecule. So as a electric field gets close to one of these entities, it can distort the electron cloud, and since it's distorting the electron cloud, it can produce a temporary dipole for something that did not have a dipole. So for example, for nonpolar molecules, the more polarizable it is, the stronger the temporary dipole moment is. So all nonpolar molecules do not have a dipole moment, but due to its polarizability, the more polarizable a molecule is, the stronger that temporary dipole moment will be. Now for polar molecules, which already have a permanent dipole moment, when you include the factor of polarizability, it's going to make that dipole moment stronger. So if you already have a polar molecule, you include its polarizability, it's going to enhance that dipole moment. So the negative side is going to become more negative, the positive side is going to become more positive. But for nonpolar molecules, which doesn't have a dipole moment, it creates a temporary dipole moment or induces a dipole moment. And the greater the polarizability of that nonpolar molecule, the greater or the stronger that dipole moment is. And so again, polarizability of particles is the ease at which electron cloud can be distorted. So again, the further apart atoms are, or the more electrons atoms have, they can easily get their electron cloud distorted. So with trends in polarizabilities, as you can imagine, smaller particles are less polarizable than larger ones, because for smaller particles, the electrons are closer to the nucleus, meaning they're more tightly held. So it's harder to distort that electron cloud. So for examples, if we're looking at cations, cations would have lower or smaller polarizability than their counterparts of their parents. So for example, if we had sodium plus and sodium, sodium plus would be less polarizable than sodium, because cations means that there's less electrons, they're more attracted to the nucleus, so it's harder to distort that electron cloud. Whereas anions have the opposite effect. So we look at, for example, fluoride and fluorine. Since fluoride is an anion, that means you added an extra electron into the outer shell, which causes the electrons to move further away, which has less of an attraction with the nucleus and more inclined to be distorted by an electric field. So fluoride would be more polarizable than fluorine. Another important thing is that polarizability increases down a group. Because if you remember from CP1, as you go down a group, the atomic size increases. Because as you go down a group, what happens? You have more electrons, which makes you have a larger electron cloud, so it becomes more easily disturbed. Now, as we go across a period, so as we go down a group, which is a vertical column, polarizability increases. But as we go across a period, it decreases because effective nuclear charge increases. So for example, if we look at, say, carbon and oxygen, which are in the same period, carbon would be more polarizable than oxygen because carbon is further to the left and has less effective nuclear charge than oxygen. Because as you go from left to right, the number of valence electrons increases, which increases your effective nuclear charge. Since oxygen has more valence electrons than carbon, it's going to have a greater effective nuclear charge, which decreases its polarizability. Likewise, if we go down a group, sulfur and tellurium, tellurium is below sulfur, so it's going to have a larger electron cloud, which means it's going to have greater polarizability. So since it has greater polarizability, it's going to enhance that dipole even more. And that's why H2Te has a higher boiling point than H2S. Even though H2S, the difference in electron activity between hydrogen and sulfur is greater, but the fact that H2Te has greater polarizability causes its boiling point to be higher. So now we'll look at some examples here. So we have these different organic compounds, and I like to use organic compounds because most people who take general chemistry 2 usually go on to organic. So at least if you see organic molecules here, it'll be familiar to you in organic if you take it. So just a few little explanations of the structures here. So anytime you see an organic compound, it's written like this. Every time you see an ending of the line or an intersection of the line, so we have intersections and we have endings. At all those intersections and at the endings are carbon atoms. And so what you have to remember is that carbon likes to have 4 bonds. So when you look at each of these endings or these intersections, if you don't count 4 lines around that carbon, then you make up the difference with hydrogen. So for example, at this intersection here, there are 2 lines. So we're missing 2, so it's understood that there are 2 hydrogens here. And this is just a more convenient way to draw organic molecules. Now you won't have to draw these. I'm just showing you how to interpret the structure. Likewise, At the end, since there's only one line, that's understood that there are 3 hydrogens coming off. So again, carbon likes to have 4 bonds, just like a cat likes to have 4 legs. So when you count the intersections, if it doesn't add up to 4, the remaining difference is hydrogens. Likewise, at the ends, if it doesn't count up to 4, the remaining are hydrogens. And there's an organic professor that always loves organic chemistry so much that she named her cat Carbon, because carbon, and then she tells her students carbon has 4 legs, just like carbon likes 4 bonds. That's just a little side note to help interpret these structures. So now, how do we determine which one has the smallest polarizability? The general rule of thumb is the greater the molar mass, the more electrons. And the more electrons means greater polarizability. And this is the general format. So again, you look at the molar mass, the greater the molar mass means there's more electrons. If there's more electrons, it causes a greater distortion. It'll be a more distorted electric field, electron cloud, which means it's greater polarizability. And so what we want to do here is determine, if we want to know the smallest polarizability, well, we're looking for the one with the smallest molar mass. So if we look here, we don't have to calculate all of these molar masses. You see that most of these have 7 carbon, 6 carbon, 6 carbon, 6 carbon, and 6. If we look at the non-carbon hydrogen atom, this one has oxygen, this one has nitrogen, this one has iodine, this one has 2 chlorines, and this one has 3 bromines. And so if you look on the periodic table, oxygen has a relative molar mass of 16, and there's 2 of them, so oxygen's contribution is 32. Nitrogen has a molar mass of 14. I mean, you can calculate the entire molar mass if you want, but this is kind of a shortcut. Iodine has a molar mass of 127. Chloride or chlorine has a molar mass of 71, 35.5, and there's 2. So chlorine's contribution is 71. And then bromine has a molar mass of approximately 80. And so there's 3 of them, so this would be 240 molar mass from just the bromine. So now you want to say, okay, the carbon and hydrogen component is roughly the same, so in order to determine the one with the smallest polarizability, would be the one with the fewest number of electrons, which is the one with the smallest molar mass. So the smallest polarizability would be B, hexane 3-amine. Because again, it has the smallest molar mass, meaning the smallest number of electrons, meaning smaller polarizability because there's not a big electron cloud in this molecule. Now, the one that would have the largest polarizability would have the largest molar mass would be the one with 3 bromines. Because remember, its contribution is 240. And you see here that compared to the iodine compound, they both have 6 hydrogens and roughly the same number of 13 hydrogen and 11 hydrogen. But since there's 3 bromines, it's 240. It's greater than one iodine, which is 127. So E would be the one with the largest or greatest polarizability. So again, we're looking when we're comparing. Now this is a general rule here. The greater the molar mass means more electrons, larger electron cloud, greater polarizability. So when we're looking for the smallest polarizability, we're looking for the one with the fewer electrons, smallest molar mass. And again, this is polarizability, not intermolecular forces. That's different. So now we get to dispersion forces. And again, this arises when we have an instantaneous or temporary dipole, induces a dipole in another, resulting in an attraction. So when you have a nonpolar molecule, such as I2, for example. So I2 is a nonpolar molecule, diatomic iodine. And so what happens is we have one molecule of iodine gets a instantaneous dipole, and since it gets an instantaneous dipole, it promotes or induces a dipole in another molecule. And so now we get this dispersion force between them. And this keeps on going, but this is instantaneous, so it can change. That's what's making it weak. Now, the thing about dispersion forces is that they occur in all types of molecules. So every type of substance, polar or nonpolar, have dispersion forces. We're not referring to ion dipole. We're just referring to the polar compounds and nonpolar compounds. So all polar compounds and nonpolar compounds have dispersion forces. It's only the major intermolecular force in nonpolar compounds. So let me write that here. So again, all nonpolar compounds only have dispersion forces. There's no other intermolecular force in a nonpolar compound. For polar compounds, it's a secondary force. So what I mean by secondary is you first look at the dipole-dipole interaction, but if that is inconclusive, maybe they have the same strength dipole, then you would refer to the strength of the dispersion forces. So that's what we mean by secondary. So for polar compounds, the major interaction is dipole-dipole. The secondary interaction is dispersion. So if you can't conclude based on the first criteria, which is dipole-dipole, then you would move to the second criteria, which is the dispersion forces. Now for nonpolar compounds, the only force present is dispersion. And so dispersion forces are stronger for the more polarizable particles. So what this means is, as we talked about in the last slide, more polarizable means more electrons, a larger electron cloud, which means greater molar mass. So the larger the molar mass, the stronger the dispersion forces are, the more polarizable those particles will be. So molar mass is a direct relationship between strength of dispersion forces. So we have molar mass and dispersion forces. So when you have an increase in molar mass, you're going to have an increase in dispersion forces. So that's how you can determine if you're given a list of nonpolar compounds. You look at the compound, if it says which one has the strongest or largest dispersion forces or highest boiling point, you would look at the nonpolar compound with the largest molar mass. If it asks which one had the weakest dispersion forces or lowest boiling point, you would look at the compound with the lowest molar mass. And so for nonpolar molecules, the main criteria for determining whether or which one is the stronger dispersion forces is the molar mass. That's the first criteria. Now with dispersion forces, you may say, well, what happens when you have two compounds with the same molar mass? What do you look at then? And we'll get to that in just a moment. But the main criteria for nonpolar compounds to determine the strength of dispersion forces is the molar mass. The larger the molar mass, the stronger the dispersion forces, the higher the boiling point. And so again, what's happening is when we have these dispersion forces is that when atoms or molecules are far apart, they can't induce the electric cloud of another neighboring entity. But when they get close to one another, then they start distorting that electric cloud, producing an instantaneous dipole. And as this occurs through the entire substance, you get these intermolecular interactions forming. But these are really weak because remember, these are instantaneous. They don't last for very long. They're temporary. And they're not uniform as they are with permanent dipoles. If you remember, for dipole-dipole, they have a permanent dipole. The distance or the intermolecular interaction was uniform throughout the entire substance. Here that's ununiform. We have all different types of interactions. So as I mentioned before, when we have molar mass is a good indicator of the strength of the dispersion forces. So the higher the molar mass, the stronger the dispersion forces, the greater the boiling point. And one of the best examples on the periodic table to show you how molar mass affects the strength of dispersion forces is the halogens. So if we take a look at the halogens, group 17 or 7A, these are all nonpolar molecules, F2, Cl2, Br2, I2. They're all nonpolar. The only difference is their molar mass. They all have the same number of valence electrons, 7. So the only difference here is the molar mass, because as you go down a group, we're adding more electrons, molar mass goes up. Since we're adding more electrons, they get further from the nucleus. They're further out. So the farther out electrons are, they're more easily polarizable, which leads to greater polarizability, stronger dispersion forces, higher boiling point. So if you look at fluorine, fluorine has a molar mass of 38. Its boiling point is 85 Kelvin, which is pretty cold. Chlorine, which has a bigger molar mass than fluorine, has a higher boiling point than fluorine. Since it has more electrons, it's more polarizable, higher boiling point, stronger dispersion forces. But both of these are a gas at room temperature because they have very weak intermolecular forces. Now when we get to bromine, bromine's boiling point is 333 Kelvin, and to give you an idea of this, 333 Kelvin is roughly say 50 degrees Celsius. So it's, bromine exists as a liquid at room temperature. So notice how when we go from chlorine to bromine, we go from a gas at room temperature to a liquid, indicating that the intermolecular forces are stronger in bromine to keep it as a liquid at room temperature versus chlorine. Secondly, or lastly, we go to I2. It has a molar mass of 254. Its boiling point is 458 Kelvin, which is almost little shy of 200 degrees Celsius. It's probably like 100 and what is it? Maybe 183, 185 degrees Celsius, but it's very high. And notice that when we go from bromine to iodine, we have more electrons, greater molar mass, greater polarizability, stronger intermolecular forces. And I2 exists as a solid at room temperature. Now, when you compare fluorine with neon, you'll see that fluorine has stronger intermolecular forces than neon, because neon is just, as we saw in the earlier part of this chapter, it's an atomic solid. So it has less electrons than F2, so it has weaker dispersion forces. Likewise, xenon has a smaller molar mass than Br2 and I2, and you'll notice that its boiling point is less than those. Even with chlorine, even though chlorine is Cl2, which has a molar mass of 71, its boiling point is greater than xenon. And so again, this is one of the times where, chlorine and xenon, you would say xenon has more electrons, but chlorine has a higher boiling point. And so this is one of those exceptions where the molar mass doesn't match up with the strength of the dispersion forces. Same for crypto. But we won't have, that's a whole nother can of worms for a different time. But namely, as you go down a group, as you increase the molar mass, you increase its dispersion forces. Now, one thing I wanted to mention here is that we have to be comparing apples and apples in regards to molar mass. So if we, for example, we look at H2O and we look at I2. Now, H2O has hydrogen bonding and a molar mass of 18. And at room temperature, it exists as a liquid. Now, if we go to I2, I2 is nonpolar. It has dispersion forces. The molar mass is equal to 254. And at room temperature, it's a solid. So the reason I bring this example, because this is when you're not comparing compounds or substances with similar molar masses. Here we're comparing two substances with really different molar masses. So you may say, well, it was mentioned earlier that hydrogen bonding is stronger than dispersion forces. You are correct, but only when we're looking at compounds or substances with similar molar masses. Whenever you're comparing two or more compounds or substances where the molar mass differs by more than 100, then we have to look at the strength of the dispersion forces. So since I2 has a molar mass of 254, which is beyond that 100 range, then we would say that the dispersion forces are a lot stronger than the hydrogen bonding forces in water. And this is confirmed by the fact that at room temperature, water is a liquid, whereas at room temperature, iodine is a solid. But you only make this comparison when the molar masses between the two things you're comparing are different by more than 100, roughly 100 grams per mole. And we all know that water has a boiling point of 100 degrees Celsius, which is 373 Kelvin. And we just saw below here that iodine has a boiling point of 458 Kelvin. So this again confirms that iodine, I2, has a stronger intermolecular forces than H2O. Because the boiling point tells you how much energy is needed to break the intermolecular forces. So again, when we're comparing two substances that their molar masses differ by approximately 100 grams per mole or more, the one with the larger molar mass has the stronger intermolecular forces, which means the higher boiling point. Because again, here we're not comparing apples and apples, we're comparing apples and oranges. This was the last topic involving intermolecular forces that I want to talk about. And again, this is a secondary or tertiary criteria when looking at substances and determining which one has the stronger intermolecular forces. So for nonpolar compounds, we said, okay, we look at, or nonpolar substances, I should say. The first criteria is molar mass. We said the higher the molar mass, the stronger the forces. That's the first criteria. For polar compounds, the first criteria is the strength of the dipole moment. Now, if that can't be the deciding factor, the second criteria was this molar mass, which is dispersion forces. Now, one may argue, what happens if the molar mass is the same? What do we look at? So we look at a nonpolar substances, and we notice that they both have the same molar mass, which happens when we have constitutional isomers. They have the same molar mass but different shape. What do we look at then? What's our deciding factor? Likewise, when we have polar compounds, if the molar mass and dipole moment are the same, what's the deciding factor? And the deciding factor is the shape of the molecule. So the more spread out the molecule is, the stronger the dispersion forces are, because the more contact points molecules can make with each other. So here we have N-pentane and neopentane. They have the same chemical formula, same molar masses. They're both nonpolar. The only difference is N-pentane is a chain, whereas neopentane is more confined. It's more compact. So neopentane is more compact, N-pentane is a chain more spread out. So the more spread out a molecule is, the more contact points it can make with another molecule, the stronger the dispersion forces are. So when you're comparing two substances where the molar masses are the same, you want to look at its shape. The one whose shape is more spread out is the one with the stronger intermolecular forces. So again, you only look at this criteria when the molar mass criteria is inconclusive. This is not the first criteria. The first criteria is the molar mass criteria for nonpolar substances. Now, if that doesn't work, then the next criteria is molecular shape. Likewise, with polar compounds, first criteria is the strength of the dipole moment, aka difference in electronegativity. If that doesn't work, we go to molar mass. And if that doesn't work, then we go to molecular shape. So you have to go in this order. You can't jump around. You got to go sequentially. So if number 1 is inconclusive, you go to number 2. If number 2 is inconclusive, you go to number 3. By number 3, or for polar compounds, or number 2 for nonpolar compounds, you should be able to determine which one has the stronger intermolecular force. Again, molecular shape is only used when the other factors are inconclusive.